Good afternoon. Now we are going to talk about Trojan detection using side channel analysis, and Dr. Korfa talked in detail about side channel analysis and attacks. Just to recap, that when you do side channel analysis, there are different types of side channel footprint. So, this example we are using a power footprint. Instead of tracking the power, if you are holding a probe, it could be electromagnetic emanation footprint. In few minutes I am going to talk about path delay footprint, but whatever it is, we are not looking at the functionality of the device, we are looking at side channel footprint. And if some computation is going on, if you can connect your supply and observe the power dissipation and plot it, you would be able to figure out what computation is going on. Using machine learning, if you kind of trained your machine learning model for different programs and different footprint, it would be able to detect what program is it. Now, in general, the basic idea, as you already know, depending on each operation in a computation takes different amount of power. It could be just a square root operation, this could be squaring and multiplication. So, you can analyze this simple thing, and when this idea first came in, basically first attack was all smart card was kind of broken the security of it. Of course, this is simple power attack. These days attackers also smart enough, they do not want to keep this footprint, they will either make this one bigger or that one smaller, but whatever it is, you can do differential power attack and many sophisticated techniques, and this is power based side channel attack, power or dynamic current based. Now, we are going to use those features to Trojan detection. So, I am not going to get into the detail of side channel aspect of it, rather I am going to focus how do we use those side channel features for kind of Trojan detection. Let us start with the dynamic current or power based, but before I go there, I wanted to show you that whatever I shown so far earlier, the statistical test generation, whether machine learning, whether direct or not direct, we call it logic testing or simulation based security validation, and side channel. If you can look at side by side from a Trojan perspective, the positive aspect or most of the aspect of simulation based security validation happens to be the negative aspect of side channel and vice versa. Whatever is positive of side channel happens to be the negative. So, this simple observation essentially led to the work that I am going to talk about, that you can combine them effectively to kind of take advantages of them, and this is a common research theme. You kind of understand two good ideas and you can put them together. So, let us touch upon one of them, what is logic testing. So, even if you have very tiny Trojan or tiny Trojan, what does that mean? Let us say trigger of only 2 gates, we call them a tiny Trojan. So, for logic testing it is a great idea, because activating a trigger of 2 is much easier than activating a trigger of 10, because the probability of activating is 1/4. Probability if you have like 10 or 20, it is like 1/2 to the power 10, that is very low probability. In contrast, in side channel it is negative problem, because one tiny AND gate with 2 input, the extra power it would consume or dissipate, that is just negligible, not even nanowatt, even like less than that. In a bigger scheme of things, when things are taking milliwatt or watt, in a tiny nanowatt of power difference will not show up, and specifically because of the process noise or process variation we talked about, that could be anywhere between 1 to 10%, let us just say 1 to 2%. That would be still in the milliwatt range. So, a nanowatt will hide easily. In contrast, if you give a big AND gate, lot of inputs, it is a problem for logic testing, serious problem, because the probability of activating goes down by 1/2 to the power n, but large one is an advantage for side channel. If there is a big gate or a lot of gates sitting there, they are going to consume or dissipate a lot of power, and if you are measuring power, you will see the difference. Any questions of how positive and negative kind of map each other? So, side channel analysis is bothered by process variation, because process variation affects side channel. Logic testing does not care about process variation, it only cares about the final output. that is all it cares about. So, if I want to pictorially present it, the test generation problem with testing, you apply some test vector. How do you generate that, how quickly you get good test? We talked about lot of algorithms, whether ATPG, reinforcement learning, Shapley ensemble boosting, how do you get this number and flip the bits, that is different. But once you do that, if you have a golden design, original or Trojan injected design, then if there is a difference, then you know Trojan got activated. But we know the real problem. Real problem is how do we get to that number that would activate the Trojan, because the input space or the test space, this space is exponential. The number of inputs that you have to try is exponential. In contrast, in side channel we actually do not care about the input space. If you recall, when we talked about simulation versus formal verification, we had this same dilemma. Here sure you apply something, but it is really not really important what you apply. What is important that you do a diff of the power signature that is coming in, and if that power signature has some difference which is beyond process noise, then it is good. But the problem we know, because number of gates are so small, the difference of power even in the most expensive oscilloscope with amplification, there is no way you can find it in reality. So, then what can we do? We can combine both of them. We can use the efficient test generation, do the logic testing, and then we can do side channel analysis. So, input is logic testing, output is side channel analysis. So, what is the key idea? Key idea is we want to maximize switching in the suspicious area and minimize switching the rest of the design, that is the key idea. Again this same thing, it relies on the threat model. Let us look at an animation to understand what is going on. So, let us say we kind of computed our error signal, these red dots are error signal, blue dots are actual design. In reality, number of red dots would be in small 4, 10, that range, number of blue dots would be in millions. Here it is not proportional. So, when you apply any input, first of all we do not know whether there is a Trojan, we also do not know where the Trojan is. In this case, let us say I told you there is an AND gate sitting here that is taking this one and that is the trigger, that is the Trojan. So, if at any test case can activate these two, then that is wonderful story, right. So, let us just run a test case. So, it just coincidentally in this test case both the red dots are flipping, switching, that is great. Switching basically means it is going to charge the capacitor, it is going to consume the power or dissipate the power, our power analysis technique will be able to detect it, but the problem is other millions of blue dots also switching. So, two red dot switching will easily hide with millions of switching. Is that true? Let us plot the data. So, this is again a silly benchmark from ISCA's benchmark suite. Even in that silly benchmark I can illustrate you this problem. So, the amount of switching of the rare gates or that we call delta switching, that is basically is this particular is basically this particular line. As you can see that when you do random versus n detect for higher n, the switching indeed increase, which is good, switching is increasing. But what is not good, look at that red one, and by the way this red one is not this dimension, it is this one total switching dimension, which this number is significantly larger. In this tiny silly example it is about 10 times larger, 10 to 20. In general this is going to be 100 to 1000 times larger, and what you observe, the switching of the main design is also increases. If it was on the same scale, maybe this is still fine, comparable, but because this is a 10 times or in this example 20 times larger, in reality 100 to 1000 times larger, this tiny increase, no matter how it looks, it increases from 10 to 17.5 in power consumption or power dissipation, is meaningless compared to these large scale of things. So, both are increasing, both are switching. So, it is not so sensitivity, the term that is used in Trojan detection is known as sensitivity, and in layman terms there is a formal definition to it. In layman terms is basically rare switching or switching off rare nodes or rare events divided by overall switching. And because rare switching is so tiny or overall switching is so large, this number is negligible. And this sensitivity is important because the device you are connecting for measuring, that device should have sensitivity to capture that. Any questions? So, then now it just turns out in that work we are able to reorder certain tests without knowing why it worked. It did work, which is analogically this Trojan circuitry signals flipped and also some of the original design signal flipped. Now, in reality you realize this picture is not possible, because from somebody to go from input to output, it needs to create event in at least one of the path. Here as if I am showing there is no activity in anywhere in the design except in that region, that cannot happen. It is going to have some activity on some path. It is basically the idea is you maximize switching in the rare or suspicious region, whatever your definition of suspicious. For Trojans it is basically rare nodes, that is one objective, and another objective is minimize switching in rest of the circuit. So, you select the or generate the test cases so that you minimize the switching basically in the design. Overall design you minimize it, suspicious area you maximize it, so that it become easier. So, in this particular case we can have an effect like this with certain kind of parameter. You can have the overall dissipation actually went down and the delta switching went up. If you can somehow able to locate this region and measure at that time, then Trojan detection becomes easier.
How conceptually it is possible to do that?
So, conceptually it is possible because you are, so first of all theoretically it is possible, practically for ISCAS benchmarks it is possible, real design we do not know. It is possible because you are trying to find the path where you can go wherever the rare nodes are. So, while you are going to this cone, you are trying to not disturb too many parts of the cone, you are trying to create switching only the few gates in that cone, and then that would create switching. So, there has to be a test pattern which is able to do that. So, the idea of the algorithm is to find such a test pattern.
So, but you have to give input to the other inputs also.
You have to give input to everything, but the thing is you want to give input that will not change the ones that are not needed for switching there. You want to choose input such that those gates do not switch. Inputs you still have to give, but it is just that think about it the way, if I want to do a controllability problem this way, you are basically trying to figure out what is the minimal changes I can do in the path to have that switching possible. That is basically the objective function.
Now, how do you identify that?
Identify which one?
Which are the, so you just take the cone of influence and how do you identify the minimum test case?
Right. So, we have some improvement on that. In this particular paper we are basically trying to start with two pair of pattern and choose the pair that have that objective function. Later we kind of improved it, but basic idea remains the same. How do you play this minimize maximize game? Two sets of elements, one has large set, another is small set. You are maximizing in a small set, minimizing in the large set at the same time. That is basically the objective. And genetic algorithm is a natural fit, machine learning is a natural fit. I will talk about both of them. So, it is basically you are trying to create minimal switching so that you can create the switch with two vector. Unlike the Trojan detection work, we are only talking about one vector. For power switching, you need a test case is a pair of vector, because a pair introduces switching. So, you have to find the first and second pair, but the problem of this one is the noise margin is really small. No matter how much you switch, the path is still long. So, how do we improve it? In our subsequent work, we basically looked at that first vector is important, but the second vector is more important. So, once you know the first vector, how do you do second vector? In the initial work we kind of looked at reordering and we got to the right answer, but why that was right answer we did not know. So, instead in genetic algorithm we are basically saying if this is my first vector, then what would be the second vector that has that objective of minimize suspicious, minimize design switching and maximize suspicious switching, and then that is basically going to do the trick. And the reason it worked, and initially we are kind of bothered why is it working. Reason it worked, although you have 200 inputs, once you know who are the rare ones, machine learning, in fact machine learning works like a charm here, and later we realized how did machine learning do better than anything else. Machine learning very quickly figures out which rare node is kind of correlated which of the input. It is like everybody is not equally correlated, they have we call it input affinity. So, which of the input has affinity to, and a minor change in input, actually if they have affinity, minor change in input will create maximum change in their switching behavior. And so, basically this is kind of an ideal problem for machine learning. For us it is kind of difficult, you trial and error, they quickly figure out, if you run few test cases, provide certain things, very quickly they figure out who is kind of have design has affinity. And because these designs are not random, they are written by people, there is some structure in it, that is why it works. If somebody came up with a random design, all these algorithms will not work, machine learning will not work, even genetic algorithm will not work. So, those are the two basically core observation, and the way genetic algorithm worked here is basically you start, once you are given the first pattern, initial input pattern, now you are trying to find the second pattern. In this example we are trying to flip one of the bit. So, there are 5 bits. So, one of them we decided to keep the same. So, we are basically trying different choices first generation, and then you are computing fitness with respect to the objective, and then you again try some mutation, selection, crossover, and do the iteration to see if you can improve over the thing, and then eventually when you are not able to improve anymore, you say you know what, this is my first test case pattern, this is the pair that I am interested in. That is basically the idea of maximizing switching through current analysis. Now, does it improve sensitivity compared to if you just do some ordering and try to do that? It definitely does. Now, here is the another thing again, when you look at another paper, it just happens to be both our paper. When you look at another paper and that kind of showed you certain number of results, and you want to show no, that is not good, then you have to say which sensitivity is measurable by oscilloscope today. Is it 10%, is it 5%, is it 2%? If like close to 1% sensitivity is measurable, 1% or less than that, then the existing work will still be able to detect Trojan. But if today's oscilloscopes are not able to do that, then basically you can safely say unless your Trojan sensitivity let us say higher than 10, existing approaches will fail. So, which one will say it has to be realistically based on what oscilloscopes are on the market, what sensitivity or what difference they can measure. Now, I am going to talk about another side channel footprint called path delay. So, path delay is basically, if you look at this sequence of gate, they are going to consume some delay. So, depending on when you apply the input and when that output would be observed, in this particular case this gate is going to take this much of time, the second gate is going to take that much of time, and so on and so forth. You can kind of figure out which gate will take how much. So, that is the notion of delay. You apply an input and that change how long it will take to reach there, and this delay itself we can kind of utilize to do Trojan detection. And I will go straight to the point, how do I do that? So, let us say this is your original golden design, this is a Trojan inserted design, and as you can see this trigger is coming from somewhere, this is your payload. Now, if trigger is not activated, then the delay difference is the delay difference of a gate only. Whatever is the delay is the time propagation time of all the gates and wires in that path. because of Trojan insertion only difference is this XOR gate, that is it, and that too if trigger is not activated, then it is going to go through the normal functionality, and one gate difference is in the picosecond difference. In a bigger scheme of things that cannot be detected by anybody, but if we can somehow activate the trigger, then not only there is a single gate, there could be lot more gates. In the payload there could be lot more gates, in the trigger there is a lot more gates. This path is totally different than this path. That does not mean delay would be more, it could be delay could be less, but it is a totally different path. Now you have two different paths, that is why there is a two different delay. When you apply the input, when you measure the output, there is a delay. So, the delay difference will help you in identify the Trojan. Now, this problem could become complicated, because if you recall, in a normal design with process variation, even the critical path sometimes take longer, sometimes is shorter. As long as this delay difference is higher than that process variation, then or sensitivity, then it is a good idea. Any question on path delay based analysis? Now, this idea of delay people use left and right in for side channel analysis for different kind of delay. Even if you recall, when I talked about cache timing attack, I have a whole day of microarchitectural attack. The cache timing attack, one of them, that is also based on this idea of delay. You access a data, does it take short time or long time? Based on that, you figure out who accessed it, then you figure out what value is it. So, you figure out the value of somebody else based on the delay. So, idea of delay, as I said, in almost every domain, and the delay based analysis like power based analysis is very stable, and because the gates and paths, all these are kind of interestingly independent different paths, you can actually measure them parallel, and there is a lot of work on delay based analysis. So, I am going to skip all the content of how all of these works. I am going to spend some time on machine learning. So, the last three work of today are all based on AI and machine learning. What I want to do show this delay based analysis, how do we apply machine learning on it? We know what is delay, there are publications on how do you do delay based Trojan detection, how do you apply reinforcement learning, and as you can see, this diagram we have seen before. Only difference is, instead of scope parameter or rare values, this is delay difference, everything is exactly same up to the point the flipping the bits, up to the point flipping the bits, everything is exactly the same as statistical tests, only thing is the delay difference is the. So, the mechanism to measure, now those of you who work in this area, you know you can control the clock, and you can control the clock and you can create two different delay. If you can control the clock, you can create two different delay, you can measure the delay very effectively, very easy actually measurement of delay. But if you cannot control the clock or change the clock duration, then delay measurement is difficult. Any question on reinforcement learning? As I said, it is exactly same, only thing changed is the delay difference. Go ahead.
What is the reward function for this?
So, it is same thing, do I keep the flip, do I ignore the flip? It is the same function. You can on top of it you can do genetic algorithm, but I am saying the core idea of reward penalty, it is exact same story.
But if you have say, how do you get two version of the design, because to get the delay difference you need two version of the design, right? But
all of these works, very interesting question, how do I get two, all of the work I have talked about so far is about we have the availability of golden design, we know how much delay it is supposed to take. In reality that is a problem, that is why I will talk about one work on golden free detection, actually maybe I will talk about two works, but all of them based on that the golden model is available, you know what should have been the delay, what should have been the output value, so that when you run this the output value is different. And again any test cases you run, whether the delay or not delay, you basically want to show for different design what is your Trojan detection rate. So, in this particular case reinforcement learning is able to get closer to kind of 80%, whereas many others when the design size increases, I know all of those are silly designs anyway, even within themselves they are increasing order, this is like about 10,000 gates. So, even the existing approaches kind of accuracy goes down pretty drastically for delay based analysis. Now, I want to talk about golden free Trojan detection. So, there are two techniques I want to talk about, and I am going to talk about zero shot learning. Maybe another technique, let me just create a W here. Another technique I am going to just write it here. So, golden free Trojan detection is the real world problem. In fact, DARPA, defense, most companies they say we have only one model. Although initially they started with a golden model, nobody kept track of it, and nobody started adding the features, either customer requested or something happened last minute, all that stuff. Nobody had time to go back and modify the original C model, Verilog VHDL model, nobody had time to do that. So, therefore, there is no golden model, even for functionality nobody has a golden model. People have only one model, whether the soft version like VHDL Verilog or fabricated version of a chip, they have exactly one. In that case, that is called golden free Trojan detection. What do you do? So, there are a couple of ideas. I am going to just talk about two. One is on self referencing, that I am going to talk about right now, and then there are tons of work on machine learning model. I will show one work on zero shot learning. In fact, machine learning is kind of used extensively in most domains when you do not have a golden reference model, because then you are kind of. So, people want to go for, if you recall, we talked about known known, known unknowns. Let me write that once for you and then I will come back. Known knowns, known unknowns, known knowns, known unknowns. Let us just put one of them, unknown, unknown. So, known knowns in the Trojan example, think of, so this is a Trojan, let me take another color. So, this, think of this as this is a Trojan and this is a 4 trigger. It is just that during your training time, the examples, the 4 signals you took as a trigger is different, and during testing time the 4 signals you are taking as a trigger is different, but it is both are known. Trigger is also known, that is we are talking about a vulnerability called Trojan, that is also known. Known unknown would be, it is still a Trojan, and again how much unknown you want to introduce, that is different. I am just saying it could be 6 trigger, it could be 8 trigger, the situation, these situations were not included as part of the training process. That is why you call it a unknown. There is an unknown parameter to this story. Unknown would be, I mean it cannot be Trojan, right, it has to be something else, I do not know, whatever that is, you think of that, and this also has to be think of that kind of stuff. So, most people are targeting AI for these two, and most companies and most countries are interested in this one, and their objective is, can you do natural language processing, read today's newspaper, tomorrow's newspaper, day after tomorrow's newspaper, and can you predict what attack is going to happen. Maybe news is not in the explicit form, maybe for human to read news all across the world is not possible, but a machine learning will read that, make some unknown dots, connect some unseen dots, that this is happening in Russia, that is happening in Iran, this is happening in India. So, I guess this is something is likely to happen. This seems to be matching something happened 30 years ago in a country Y. So, whatever it is, that is basically people, and this is completely AI territory. Although I am taking only example of Trojan, but that is the key idea that you want to go after. Now, let me talk about self referencing for a moment. If I do W, would it, let us do self referencing here. So, in self reference, now if I do, I have to, let me try okay another. So, the idea of self referencing is, when you do not have a golden model, can you compare with yourself, you yesterday versus you today. You do not compare with anybody, you do not get stressed in life, How did you do yesterday, how did you do today, that is the closest analogy. But in real life, think of a processor, you are doing Trojan detection in a processor, right, and processor has two ALU, ALU 1 and ALU 2. Now, the idea is you generate test pattern in such a way, so that it applies to ALU 1, it applies to ALU 2 and you compare the output. I always use exclusive gate to just say, but you just dump the value and compare. Whether it is a functional value, whether it is a power side channel, delay, whatever it is, that is what you try to do. That is the basic idea. Of course, there are lot of intricate details and question. For example, if you take any real world processor, you try forcing on ALU 1, it will work. You try forcing on ALU 2, it will not work, because if ALU 1 is free and not hot, the instruction you cannot push to ALU 2 from the external port I am talking about, because the internal logic is that way. The if then else statement somebody wrote that way, you can't bypass it. So, there are practical limitations, but the key idea is if there are self similar components, self similar functionality at whatever granularity level, can we create test patterns, so that we activate those self similar components and compare their output in some form. So, that is one line of work. Then the line of work I am going to talk about is zero shot learning, and it uses that advantage of zero shot learning. What is the zero shot learning, anybody remember? Machine learning, you train and test patterns, or the thing you test in real world has to be similar to the things it has seen during training. If it is different, you trained with horses and asking for zebra, it is not going to work, right. Anybody remember what is one shot learning? You train for a long time, but you are asked to apply in a domain where you will be given an hour a day, not same amount of time as before. Can you provide enough information quickly, so that it kind of work? And the idea of zero shot learning is you train in a domain, in this case it happens to be animal, it does not have to be animal, and then you take that model, put it in another domain, you would not be given any opportunity to train, not even 1 hour. How would you perform in that domain? And zero shot learning claims is I will perform as good as if I was trained in that domain. How does it work? I will give you that insight. I talked earlier today in the Trojan context, I will give you the insight, but zero shot learning is I do not need to train. I know I have been to Japan, been to Korea, I am going to go to France. I do not need that, no, learn that language, I can manage, right. So, that is the idea. So, how does it work for Trojan detection? Remember, we are trying to still achieve golden free using zero shot learning. So, before that, if you recall, we talked about supervised learning. Supervised learning, you provide test cases, you provide label during training time, machine learning builds a separator, then you give a design which may or may not have Trojan, and you are asking is it Trojan infected or is it clean. So, it is able to detect, that is supervised. Unsupervised, you are basically some kind of distance metric, either you are with me, my friend, or you are my enemy, some kind of circle gets created, either you are in that circle or you are outside the circle. If that notion, you do not need any training, you do not need any label, actually I am flawed, you need training, but it is just that you do not need label data, it just kind of figures out which are similar. And once it figures out, it kind of then you give a test token, is it inside the circle or is it outside the circle. So, that is basically unsupervised learning. So, what we are basically trying to do here is a combination of them. By the way, the zero shot learning idea is a well known idea, it is there at least 10 years if not more, actually more than 10 years. So, the idea here is that we pre-train the model using supervised learning, then you give the target your design with Trojan and it makes the correct decision. Why is it golden free? Because the one you pre-trained with, it could be ISCA's silly benchmarks. This is still label data, but it is ISCA's data. If a company taking this model and they never shown any of their designs, they give just their design. That could be a million line design from some company X, and this could have been some designs from. And the reason it works, because it is able to figure out similarity, something that is similar, something that is dissimilar. And we talked about this similarity. This story is well known, and even in online there are a lot of ML model that are trained with handwritten digits. So, if there are trained with you can train also, you can take a blank model, zero shot learning model, you can train them in handwritten digits and ask them to classify apples and oranges, it will do for you. It basically figures out what is similar, what is dissimilar, that it figures out, and then it would be able to do that. So, same thing, you give a big large design, golden free one design, it will tell you whether it is malicious, benign. So, this idea works for Trojan detection, this idea works for malware detection, this idea works for everything, because after all it is zero shot learning. But if you really want to do Trojan detection, your accuracy would be significantly higher if your pre-training is on Trojan detection. It is little bit of cheating, but it is still golden free, right. So, but I have to say for the disclaimer, because it makes use of unsupervised learning, it inherits all the problems of unsupervised learning, which is basically metric learning. Which metric? Remember, it is drawing a circle, somebody similar, somebody far. So, there are lot of kind of similarity metrics, distance of Euclidean distance one of them, and as you can see, depending on the design, even for silly design, the changes, some metric is does good, some metric does bad in terms of accuracy. And there are some well known metrics, including Professor Mahalanobis from ISI in his name. So, Mahalanobis distance and all that, very widely used in statistics domain, even in machine learning, lot of people made use of it, and that seems to work very well compared to other distance matrices. If you studied statistics, you would probably know. And in terms of accuracy, the zero shot learning tend to give reasonably high accuracy. Is there a scope for improvement? Absolutely, but if you kind of course remember, it is a the known important part is known and unknown is the important part. Okay. So, if I go and trace, if you look at the SVM, known is known is 75% accuracy, but unknown is 59%. That is pretty much like a random guess. If you go to random forest, it is 70%, which is not great, but 32 is like worse than random guess. And this particular one is HTNet, which is one of the state of the art, it still goes down, and the zero shot learning from 97 it still goes down, but kind of 93%, very good. There is still scope for improvement. If you can go up to 100%, that would be kind of amazing.
So, regarding this zero shot learning based Trojan detection, so far in your golden model you mentioned that you finally give me a test case, right, that will identify the Trojan or the kind of trigger of the Trojan, right. So, but here what kind of output it will give, your model will give?
Model will say, is it Trojan infected, or it is a Boolean out, like classification.
You do not identify, right? Local,
yeah, it is just a cat or dog, just it is a classification based algorithm.
Okay. So, you do not identify where it is?
No. For that you have to do Shapley or something, then it will give you the ranking. The final idea that I wanted to talk about, now that attackers know you are making use of AI for your Trojan detection, we introduced the idea or term called AI Trojan. How would a Trojan in the AI model can be, which will obstruct from a defender from detecting hardware Trojan, AI Trojan to kind of stop hardware Trojan detection. How would that look like? We kind of explored this idea, and the idea, basic idea is very simple. We still have normal training module, and then based on the feature, remember in the stop sign we had that yellow sticker, we had to identify something similar to that, and then we kind of build another model and merge them, so that nobody can identify it, right. And then there are, over the years there are techniques, how do you get rid of. So, in this picture I have drawn them in red, so that you kind of see just for illustration, but in reality nobody will do. So, then I have normal feature and backdoor feature for the same design. So, the backdoor, if you do not worry about the word backdoor, think about it, that is also a machine learning model, that is also trying to achieve something. it is just their objective is different. First one is objective is accurately predict, second one objective is accurately mispredict. They have competing requirements and then you merge them together, but that is not enough for a Trojan. When you put it in, nobody should be able to find it or remove it first. Second is, until I put the trigger condition, which happens to be another input, in case of vision application which happens to be an image, could be yellow sticker, it would do perfect prediction. So, this top model would be active all the time. Unless I put the trigger, then bottom model would be activated. Let me see if the animation works. So, let us say it is a handwritten digit 7 and there is a tiny smudge here. So, if this smudge, so for the 7 when you are training, some model gets created, some neural network gets created and it would predict correctly as level 7. But now with this smudge I am building a model just with the smudge. I decide what is the backdoor, I decide it could be a smudge, it could be some pixel values embedded on top of it, whatever it is, I build a model and then I merge that model, right. So, here if this trigger is there, that smudge, that little bit of white spot that you can see there, if that is there, it is going to label it as 8. But if you are giving a picture during testing time and that spot is not there, then this should be disabled, this should not be activated, the top one would be activated and you are still going to get 7. So, that is it is exactly behaving like a Trojan and so basically it is similar to hardware design. We thought it is similar to hardware Trojan and we are doing on it on the machine learning domain, we call it AI Trojan and that is basically, if we have things like this, the model you are developing for detecting hardware Trojan, it would actually stop you detection of hardware Trojan. If I provide some smudge or some specific circuitry in the design, if I add little bit of extra malicious modification, it would be, even if there is a Trojan, if I add little bit of extra circuitry, extra logic in the design, it would identify it as a Trojan free. That is basically the catch, because then this part of the logic would get activated. Now, so the as I said, if you, because it is a Trojan, you have a trigger model, it has a payload model, but the way in AI community they talk about it, they call it backdoor features or backdoor model. So, basically normal model would be trained in a normal way, backdoor or payload model would produce, when payload model is activated you produce incorrect label. And if you look at the attack success rate for different types of models, the attack success rate goes if you do reasonable number of mutations, it goes close to 100%. So, this attack would be 100% success rate. That means 100% success rate basically means all the Trojan infected design would be marked as Trojan free, all of them. If you give 100 examples, all 100 would be indicated as Trojan free. And by the way, this idea works on any domain, it is not just Trojan, we applied it on Trojan, published on it. So, what are then defenses for this? So, there are many defenses in the community and as I said, every year 12,000 papers get published, there could be more, but I kind of divide into 3 broad categories: backdoor mitigation. So, pruning, the key idea is if I am adding some extra ML model into the system, exactly the way recall when we were creating trigger in a hardware design, we have a sequence of AND gates and if I find a chain of AND gates, then can I get rid of those attacks. So, similar analogy does exist in the machine learning community, that if you have certain pattern look certain way, can I get rid of it. So, that is basically the pruning and I am going to briefly talk about the first two. Then backdoor elimination is kind of neural cleans and artificial brain simulation, then trigger elimination is strip. It would not get rid of the whole model, but it will just get rid of the, identify the trigger and get rid of the trigger. Let me talk about just first of them little bit. So, pruning basically means you have a model, again you do not know which one is original and which one is thing, but based on certain idea and knowledge they will be pruning certain connection, pruning certain neurons and it would have same kind of attack accuracy as the original model. and Bayesian neural network, unless you made use of it, it is same as neural network. In neural network you have a weight, a number, a value, integer or floating point. Here you have a probability distribution. So, the way probability distribution work or they are merging and all that, it is basically very difficult to push this AI Trojan attack on Bayesian neural network. That is pretty much all I have. Thank you.